And here we go with part 3 of OpenCL. Let's talk about actually creating an OpenCL program. And you have this in code. And the numbers that are here, these are the step numbers. These are in the comments. Whoops. These are in the comments of that program. And so as we go through the nuances of all of this, it will match what's in the code. Okay. Yep, you certainly do need program headers. All these are the things, whatever you use for your C, your C++, yeah, keep them there. I always put in the openmp.h as well because I use the openmp tick functions, the timing functions to time the OpenCL program. It's as good as anything I've found. And you want to include cl.h, I give you cl.h so you don't have to worry about it. Just put it locally. Okay, allocate the host buffers. And by the way, this is going to be the same example as we saw in CUDA, just translated to OpenCL. And so we're doing A times B gets put in an array called C. We have to create the host arrays. In the CUDA example, I made them global variables. Here I'm putting them on the heap. Doesn't really matter. But what matters is don't make them local. Like don't inside the main program, don't say float HA num elements, because generally stack space is limited. And if you're using a GPU for some data parallel computing, chances are you're solving a pretty big problem. Otherwise, why are you doing this? So you don't want to make these local. They'll overflow the stack. Most of the time, if you make it too big, the compiler won't even compile. It'll just give you some error message. You have no idea what it means. So on the heap, global variables, not on the stack. And here we fill it. Like I said, I like doing the square root because then when I multiply the two array elements together, I know what the answer should be. It should be float of I. Here is the array size. We're going to need that later. Yep, we're just going to set up the status here. Oops. Creating a context. A context is sort of the set of variables that allow you access. Okay, it's not anything you can do anything with, but you need it because other calls are going to ask for it. And so, yeah, let's do that. We have one device. And by the way, I'm assuming by this point you've figured out what platform and device you're going to do this on. And I have some code about getting the proper, trying to figure out the proper OpenCL device, and I will give that to you. Basically, it looks through all the platforms, all the devices, and kind of says, okay, which is the most powerful? And that's the one I want to use. So I'm assuming you already know that. You've got the platform, you've got the device. So you're going to pass in the device identifier, and you are going to um, create the context. And it's going to put the status right here, not the return value. In this one, there's a real return value. It will give you back a data structure that is the context. So sometimes the status comes back as the return value. Sometimes the status is in the argument list. Now we're going to create a command queue. We'll talk about command queues in a moment, but here's the context, here's the device, there's the status, and back comes this thing called a command queue. Now we're going to create the memory buffers over on the device. We used CUDA malloc for this before. Here we're using create buffer, but here come device A, device B, device C. They are something that will tell your code where these arrays live over on GPU memory. And just in case there is special read-only or write-only memory over there, you're allowed to give it this hint. As far as I know, nobody actually uses that hint yet. Who knows? Um, one thing about that read only and write only. That terminology is with respect to, well, the GPU, with respect to the OpenCL device. And so what we're saying here is the array called A is going to be read into the GPU. The array B is going to be read into the GPU. The array C is going to be written from the GPU. So get the direction of the terminology correct. All right, write the data. We did that before, but with the CUDA mem copy, here it's in Q write buffer. Here's the command Q to put that in, and here is the device memory, and here is the host memory, ready, go. And there is a separate NQ write buffer and an NQ read buffer. So it's not like in CUDA where you've got to get the order right. Here, yes, this argument is on the device. This argument is on the host. Now, what is this command buffer? And why the word NQ in here? OpenCL works on the idea that there is something here able to accept commands, and you stick your commands on a conveyor belt, so to speak. And that's what NQ means. So Q means putting it on a conveyor belt. I think of this as like a Pac-Man, wabba, wabba, wabba. And it's just gobbling up commands that are on the conveyor belt. The reason you do this is you don't have to wait to find out if OpenCL is ready. You just put it on the conveyor belt. Who cares if OpenCL is too busy to do it right now? It will get to it when it gets to it. Also, if OpenCL suddenly decides it's busy and has a lot of time, it can be gobbling these things up as fast as it can. So in some ways, this queuing, this conveyor belt, acts like sort of a buffer between you and OpenCL. You can put things on the belt at your speed. It can gobble things off the belt at its speed. You don't have to wait on it. It doesn't have to wait on you. So that's why it uses the word in queue. So anytime you see the word in queue, that's what you're doing, is you're putting it on the conveyor belt. And that's why we needed to create that command buffer. That essentially is the conveyor belt. Okay, let's talk about the separate GPU file. So here is the entire .cl file for this application. Okay, array mult, we're declaring it to be a kernel function. And here are the arguments. They're global memory pointers. Okay, these we're going to call const because we're not going to change them. Again, that's just sort of a signal to the compiler. There's a built-in function call to get the global ID. You don't have to multiply thread numbers and block sizes and stuff. The 0 means we're getting the X value. It could have been .x, .y, .z. It's not. So it's a 1D problem. We only need the X. And so in this large set of arrays, that's the one we're working on right now. That's what'll come back. So this will appear as thousands of threads, and each thread is going to have a different GID. We do the arithmetic, and that's it. Now, the OpenCL code is compiled in the driver. There is not a separate external compiler for it. There can be. There is a new feature now in OpenCL where you can compile it externally, but originally, and it still works this way, you can just have it compiled in the driver. So the compiler comes with it. The driver gets installed, there's a compiler there. Okay, so somehow we're going to have to hand this into the OpenCL driver to have it compiled. Now, if last quarter you were with me in the shaders class, we talked about the way that shaders go about this. The mechanism is exactly the same in OpenCL. It's an advantage of having all these people, in the Kronos group be on the same standards committees. Is the way that OpenGL shaders does it is exactly the same way that OpenCL does it. Yep, this is the same kind of diagram that we used in the shaders class. Okay, but here's what you do in case you weren't in the shaders class or in case you've forgotten 4 weeks later. You read the kernel code, that file, that .cl file, you read it into an array. Yeah, you open the file name, you seek to the end, that tells you how many characters are in the file, you create a character array of that size, and you read it all in. Boom. Oh yeah, right. Um, if you use something like WordPad to type in your shader code, but then you bring it over to Linux, Windows likes to put an extra carriage return at the end of each line, and Linux doesn't know what to do with that. I've heard that if instead of making it an ASCII read, you make it a binary read, it'll be okay. But there are other ways. We covered these in the project notes. There are other ways of getting rid of that extraneous carriage return. You can do it like this. You can do it like this. The way you know that it's there is you get an error message from the compiler that is so cryptic that it can't possibly be anything but bogus. Well, okay, that's kind of a clue that it is so confused. And yeah, that extra carriage return makes it so confused. It really shouldn't have taken any effort to write the compiler such that if it sees that, just ignore it. But for some reason, it wasn't done that way. Okay, this is a new way. It's not the new way because you can still use the old stuff. It doesn't replace the old stuff, it augments it. But if you want to, you can get the SPIR-V external compiler, and it's the same one that Vulkan uses. And you compile your OpenCL source into this intermediate format, and then the driver only has to compile the intermediate format. Software vendors love this because they don't have to ship their source. They can ship just the intermediate format, which, by and large is going to be hard to reverse engineer. But anyway, it's there. Okay, but let's assume we're not doing that. Let's assume we're going to read the whole source in and compile it in the driver. Yeah, create program with source, build program. This is how you get the error messages back. Print them to the console window or something. You do this with an array of strings, and you can put all the text into one string, and that's fine. And there's two ways to make that look correct. But they do it like shader compilation, they do it with an array of strings. And the reason they do that is supposing you've got some commonly used functions that you use in all your OpenCL code, you can bring those into a separate string. So you've got your code in one string and some commonly used functions in another, and maybe you've got some pound defines in another one. That's why they do it this way. Ultimately, it all gets concatenated together before it gets compiled. Yeah. Okay, now you create the kernel object. So you've read it all in, you've compiled it. Now you're going to declare that to be the kernel. And here is the entry point. So if you have multiple functions in that .cl file, here's where you tell it, here is the entry point for the real kernel. You also have to set up the arguments. This is one of the things I like about CUDA, is because CUDA has the C program and your shader or your OpenC or your GPU code right there. They know about each other. And so it knows how to make the function call into your GPU call because it can see it. Here you can't. So here you have to set up the arguments. Okay. Oh yeah, DA. that's the first argument. DB, that's the second. DB or DC, that's the third. Okay, again, the C program does not get to look at the .cl file, and so you have to tell it something about what is in the .cl file. And now you enqueue it for execution. I use this function called wait, and I'm going to show you what that function looks like when we get to the event notes. But for now, just assume it's okay, wait till you're quiet. Wait till everything is done over on the GPU. Let's enqueue the kernel, put it on the conveyor belt, wappa, 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 eaten up by whatever's on the other end. And, that's it. I mean, that's it. You have to tell it in that call what you want your global work size to be. That is what array sizes for the work groups, what array sizes for the work items. This is like what goes inside the chevrons in CUDA. So it's the same information. The GPU needs to know the same stuff so it can set up the work groups and the work items over on the GPU side. So this is the end of the third part. Come on back and we will wrap up the OpenCL discussion.